Okay, because I wanted to record to the cloud rather than my computer because that makes it easier to get the video shared. But all right, so welcome everyone. Happy October. Welcome to this month's Friends of Lunar Volatiles meeting. And our presenter today is soon to be Dr. Andrew Wilcoski, who's going to be talking about some of his work on modeling the delivery of lunar polar volatiles through volcanic eruptions. And so, Andrew, I'll let you share your screen and feel free to start whenever you're ready. And in terms of questions, would you prefer if we interrupted you, or would you prefer if we waited until the end to ask any questions? Either is fine.
I'm happy with folks interrupting me. That's totally fine.
Okay. All right. So folks have questions, feel free to unmute or to drop questions in the chat. And we can, if you, Andrew, if you see a question in the chat, feel free to either address it then, or we can come back to those at the end as well. Other than that, I'll just remind everyone, unless you're speaking, please stay muted. And Andrew, take it away whenever you're ready.
Awesome. Yeah, thank you. Yeah, so I'm going to give you folks an overview of this project. That's one of 3 projects that ended up in my dissertation. One of the projects is about Mars, so I can't talk about it here. And the other one is actually has to do with lunar volatiles in pits and caves. And I'm going to be talking about that at the Polar Volatiles Conference in a couple weeks, so stay tuned for that. But this project has to do with polar ice accumulation from volcanically induced transient atmospheres on the moon. And before I get too deep into background or anything, I'm just going to give you a quick overview of what we actually did with this project. So essentially, we created a model that models volcanic outgassing on the ancient moon and the ice accumulation that could have been happening in tandem with that outgassing. One of the major inputs to this model were lunar temperature maps from the Diviner instrument on LRO. And we essentially use this model to try to answer the question, could volcanism have supplied any of the water we currently observe in lunar ice deposits? And if so, where would that ice have gone and how much could have accumulated? So I'm not going to spoil the answers to those questions just yet, but this is generally where this talk is going. Now I'm going to backpedal a little bit and just talk about some of the broader context. And for this particular group, a lot of this is probably review and already known, but I think it bears repeating, so I'm going to get into it. So when it comes to the context, the moon is kind of all about context. And I show this picture because I think the history of lunar exploration has always been very much about context, and especially since the Apollo era, the moon has been this really cool laboratory for us to explore questions about our solar system, about the Earth-Moon system, and then, of course, about the moon itself. The moon has taught us a bunch about the solar system, from ages of solid surfaces, understanding of the impact processes, space weathering, regolith formation, orbital mechanics, and a lot more. And we're in this really cool time period where now that we know that there's ice on the moon, you have this new window into lunar history and the history of the solar system, because we know that ice always tells a story about a body's climate. But it wasn't always this way. So we used to think the moon was dry, and here I'm using the collective scientific we. And we used to think this for a lot of really good reasons. So water should be easily photoionized on the lunar surface and allowed to escape. Its low molecular weight would mean it could readily escape. Illuminated lunar surfaces can get extremely hot, making water very unstable. The thinking for quite a while, and even still to some degree, is that heating during lunar formation could have removed most or all of the volatiles from the lunar interior. And in tandem with the fact that previous techniques couldn't identify indigenous water in Apollo samples, it led to the understanding that, okay, the interior of the moon is probably pretty dry. So these are all really good reasons why we might think that the moon is dry. And obviously us in this group know that to be different. But some scientists suspected otherwise. Back in the 60s, Watson, Murray, and Brown predicted these permanently shadowed regions at the lunar poles. Basically, their reasoning was that because of the low obliquity of the moon and because of polar topography, there should be these regions at the poles that never see sunlight. And therefore, these regions should be very cold, and they should be potentially cold enough to trap ice for billions of years. Now, fast forward to the present day, and we have some really excellent, a lot of really excellent data sets for the moon. And one of them is these diviner temperature maps. So these are maximum annual temperature maps that I'm showing you from the diviner instrument on board LRO. And I'm showing you the South Pole on the left, the North Pole on the right. And these maps extend down to about, they extend down to 60 degrees latitude in either pole. And one of the really interesting things about these maps is you can see these very dark regions close to the poles that have temperatures that never exceed very low temperatures. The coldest of these regions have temperatures that never exceed around 50 degrees Kelvin. And these are areas where these really cold areas are correlated with these PSRs that were predicted by Watson et al. In 61. And they're cold enough for ice to be thermally stable on billion-year timescales. Now, just to define what I mean by thermal stability, I mean that at temperatures below around 110 Kelvin, it would take about 1 billion years to sublimate a millimeter layer of pure ice. And I've highlighted those areas below 110 Kelvin in white on these maps, so you can see where those are. These little areas close to the poles. But beyond the fact that these cold traps exist, and we know that water could be accumulated in the lunar poles, we know that water does exist at the lunar poles because we've observed it. We've observed it using a variety of different methods. And in addition to this, we now know that Apollo samples are much wetter than previously thought. And this is essentially because techniques for analyzing these samples have gotten a lot better. But there's still a lot of questions here. For instance, why do these methods sometimes disagree about where this water ice is? And perhaps most compellingly, where did this ice come from? So this question, where did this ice come from, is a big motivator for the work that we've done here. And as everyone here knows, it's a big motivator for a lot of the work being done on lunar volatiles right now. So where did it come from? Well, there's a couple different mechanisms that could have delivered ice to the lunar poles. The first and maybe most obvious, depending on who you are, I guess, is impact delivery from asteroids and comets. So there's plenty of evidence on the moon for impacts, kind of the entire surface of the moon. And we know that some of these impactors should have had significant water contents. Another mechanism is solar wind ion implantation. This is essentially solar wind hydrogen ions impacting the lunar surface, interacting with existing oxygen and creating OH and H2O. And then a third mechanism is volcanic outgassing from the lunar interior. This is essentially volatiles being released from the lunar interior, some of those volatiles potentially being water, and that water accumulating on the lunar surface. And this third mechanism, obviously, based on this title, is going to be the one that we're focused on here. Now, each of these mechanisms has its own nuances, such as when it would would have been most important for delivery, where ice might end up in any one of these situations. But most of the work that's been done to kind of constrain the total amount of ice delivery from each of these methods has been done for the first two methods. And that's really because volcanism has only recently been kind of reconsidered as a potential source for this water ice. And again, that's related to the fact that for a long time, we thought that the lunar interior should be very dry. But after it was established that Apollo rocks were much wetter than previously thought, and that the pre-eruptive water contents of these volcanic volatiles might have been significant. Needham and Kring in 2017 came out with this paper where they suggested that volcanism could have formed an atmosphere around the ancient moon. And essentially, they said that the peak mass of this atmosphere would have occurred around 3.5 billion years ago. And at this peak mass, this atmosphere could have lasted for around 70 million years and achieved surface temperature or surface pressures similar to that of present day Mars, which is really exciting. And so this is the work that really, I think, got a lot of folks kind of interested in the idea of volcanic atmospheres and potential volcanically sourced ice again. Now, Head et al. In 2020, I saw Jim. He's here in this room right now. Head et al. In 2020 kind of came along and said that, well, it's probably actually more likely that instead of kind of a few really large eruptive outgassing events, it was more likely that you had a lot of smaller eruptions that occurred over this 4 to 2 billion year period. So they said about 30,000 to 100,000 eruptions over this 2 billion year period. But one of the exciting things about these atmospheres that these eruptions could have created is that these atmospheres should have contained some water content. And so that got our group thinking about how much of this volcanic water could have been cold trapped and where exactly would it have gone. And so these are the main science questions that really, drove our work. So I know that was a lot of background, probably a review for most of us, but here is really where our group's work comes into play with this story of volcanic water. So just to remind you generally what we did, we created a model, we input lunar temperature maps to that model, and we used it to try to answer some questions about the ice that could have been supplied due to volcanism. So now I'm going to talk about some details of our model. So our model has three main components, and I'm going to kind of walk you through them. It's modeling all these different components throughout time. So we model around 50,000 eruptions that are occurring over this 4 to 2 billion year period after the work by Head et al. In 2020. And you can see this kind of eruption frequency distribution that we are using in the bottom left there. And most of these eruptions are occurring in that the first billion years of that 2 billion year period. So after an eruption occurs, an atmosphere is created, a carbon monoxide dominated atmosphere. And these eruptions are generally occurring quickly enough that we assume that all of this mass is outgassed in one of our model time steps, which is 2 years. Once the atmosphere is created, that atmosphere will have some initial water vapor pressure. And we are assuming that it's a well-mixed atmosphere, meaning the water vapor pressure should be the same everywhere on the moon. And this actually turns out to be a pretty good assumption based on some GCM modeling that Alanov in 2019 has done. So after this atmosphere is created, there's two things that can start happening to it. The first is atmospheric escape starts to occur. And we model 3 different mechanisms of atmospheric escape based on this work by Tucker et al. In 2021. The first mechanism is Jeans escape. So this is kind of your standard thermal escape. Molecules like water will have enough thermal energy to have escape energies in the upper atmosphere, essentially. The second mechanism is photodissociative escape. This is essentially solar photons hitting a molecule like water, breaking it up into its constituent parts, and those parts having the energies to escape. And we actually model photodissociation for both water and carbon monoxide in our atmosphere, the two major atmospheric constituents. The third type of escape is sputtering escape. And this is essentially solar wind ions hitting molecules in the atmosphere, imparting them with escape trajectories and energies, knocking them off into space. Now, simultaneously with atmospheric escape, we're allowing ice accumulation onto the surface. And ice accumulation at any particular point on the surface is going to be occurring at a rate that depends on three main things. The surface temperature at that particular location, the water vapor pressure of the atmosphere, and the diffusivity of water very close to the surface. So essentially, how efficiently water can diffuse from the bulk atmosphere through a very thin layer very close to the surface so that it can actually reach the surface and accumulate there as ice. So just to sum up again, an eruption occurs in our model, creates an atmosphere. Atmosphere escape begins occurring, and escape is going to keep occurring until that atmosphere becomes non-collisional, essentially. At the same time, ice accumulation is occurring, and that ice accumulation is going to keep occurring until either the atmosphere runs out of water vapor or it escapes totally, whichever occurs first. All right, now I will just show you the last main input to this model, and that is these Diviner maximum annual temperature maps. So again, I'm showing you maps down to 60 degrees latitude from the poles in the south on the left and the north on the right. One important thing to note about our use of these Diviner temperature maps is that we're making the assumption, that's a reasonable assumption, that the surface topography of the current moon is similar to what it was on the ancient moon. So that's important to note. But another thing to note here is that we also adjust these Diviner temperature maps to account for 25% lower solar luminosity on the ancient moon, in the ancient solar system. Now, what we can do with these maps is essentially we can treat each pixel in these maps as a potential ice reservoir. So each of the pixels on this map are going to accumulate ice at a rate based on the surface temperature there. So essentially every pixel on these maps is coupled to the bulk atmospheric water reservoir. Now, without further ado, I can show you the output of the model. So let's get into some results of this modeling work. And one of the first results we see is that in our model, ice ends up accumulating very quickly. So let me kind of break down this plot on the right for you. What I'm showing you is vapor mass on the y-axis over time, so over this 4 to 2 giga-anna period. And the blue curve is showing you the total atmospheric mass, and the orange curve is showing you the water vapor mass in the atmosphere. So each of these spikes you're seeing is an eruption occurring. Now, in this kind of zoomed out mode, you're mostly seeing just the biggest eruptions. So if we look at this inset, we can kind of zoom in and look at some sort of typical eruptions and how they behave. So let's look at this one on the right, for instance. You see that an eruption occurs, the atmospheric mass spikes, and then very quickly the atmospheric mass decreases again. And that's because water is being removed from this atmosphere very quickly. And you can see that because this orange water vapor curve is very, very narrow. After water vapor is removed from the atmosphere continues to gradually escape until it's completely gone. So we're finding that for a typical atmospheric mass for an average eruption, the lifetime for these atmospheres is around 2,500 years. And it's interesting to note that at the kind of peak eruption frequency, so during peak volcanism, these eruptions are occurring on average, 22,000 years apart. So these atmospheres are not typically going to persist between eruptions. We also see that water tends to be removed from these atmospheres on timescales of about 50 years, so much faster than the atmospheric lifetimes. And water is being removed from these atmospheres via two mechanisms. The first is ice accumulation, and the second is photodissociative escape. So now on this bottom plot here, I'm showing you the water removal rate from the atmosphere via ice accumulation in purple and via photodissociative escape in yellow. And if we look at the inset again, we can actually see that the size of an eruption controls which of these mechanisms dominates ice removal or water removal from the atmosphere. For a larger eruption, ice accumulation dominates over photodissociative escape, like this instance right here. For a smaller eruption like this, photodissociative escape actually dominates over ice accumulation. But we find that on average, ice accumulation is significant enough that around 41% of the total erupted water vapor content over this 2 billion year period ends up being accumulated as ice. So a significant amount of ice. Now I can show you where this ice ends up accumulating. And surprise, it accumulates at the poles. So now I'm showing you maps of ice thickness after this complete 2 billion year model run. And again, these maps extend down to 60 degrees latitude, but most of the action is happening above 80 degrees latitude in either hemisphere. So I'm just going to zoom in on that circle of these maps. Now I'm showing you ice thickness above 80 degrees latitude for the south on the left and the North Pole on the right. And as you might expect, the ice ends up accumulating in polar cold traps. But one of the interesting things here is that the thickness of ice depends on the temperature of those cold traps. So the colder the cold trap, the thicker the ice deposit it's going to accumulate. And that's because the accumulation rate depends so strongly on temperature. And in these thickest deposits, you're getting ice thicknesses up to 400 meters. So a lot of ice. That's happening in these kind of mega cold traps, these, kind of Three Amigos style cold traps. The average ice thicknesses across all of these ice deposits is about 50 meters. And that's kind of this, dark purple color that you see in these regions surrounding the major cold traps. And an important thing to note here is that these maps are showing you the net ice supply rate from volcanism. So we're not considering any processes here that would destroy or bury ice, such as micrometeorite bombardment or regolith mixing. But one thing we can kind of do to get at the thermal stability of these ice deposits is say, okay, assume that once these ice deposits are deposited, they're going to remain exposed to space for 4 billion years. How much of this ice is going to sublimate away to space? And we find that even if we allow sublimation to space over 4 billion years, a lot of this ice ends up remaining. This is kind of an extreme case because much of this ice should be shortly after it's in place, should be mixed up with regolith or buried or potentially even destroyed by these other processes. But this map shows you kind of the thermal stability of these deposits. Another interesting result of this model is that the fractional area of ice that's covered by ice increases as you approach the South Pole, but the same trend does not exist in the north. And that's what this figure on the left is showing you. So it's showing you fractional area of ice with latitude band approaching the pole in either hemisphere. The blue curves are for the south, the orange curves are for the north. And the reason there's such a strong trend in the south is a direct consequence of the fact that the cold trapping area increases as you approach the South Pole, but it doesn't increase as you approach the North Pole, at least nowhere near as strong. And one of the reasons this is interesting is because a similar trend was noticed by Rubinenko et al. In 2019. Basically, they found that simple craters tended to get shallower as you approached the South Pole, but not the North. So these two plots I'm showing are from their paper. They're showing you the depth diameter in the North Pole on the top here. You can see there's no trend. And the depth diameter in the South Pole. You can see these craters tend to get shallower as you approach the South Pole. They interpreted this observation to be evidence of the infilling of these craters with ice deposits. And they estimated that the maximum infilling depth of these ice deposits would have been 50 meters. Interestingly, our modeling is consistent with this observation, and also the average ice thickness predicted by our model for deposits is also around 50 meters, which is compelling. Now, I think I'm doing decently on time, so I'm going to mention one last little tidbit from our modeling that's kind of interesting. One thing we find with this modeling is that while one of these atmospheres still has a significant water content to it, a frost should actually accumulate on the lunar night side. So what I'm showing you in this plot is latitude on the y-axis and time over 2 lunar days on the x-axis. And I'm showing you frost thickness. And I want to call your attention to the color bar here. We're talking about tens of microns of frost thickness. So very, very thin layers of frost, but still optically thick. So still, you could still be able to see this if you're around 3 billion years ago. So what happens at the beginning of one of these shorter model runs is frost begins to accumulate at all latitudes on the night side, and then sunrise occurs, that's this dotted line, and frost begins to ablate at the lower latitudes. You go throughout the day where nothing happens, and then at sunset, after sunset, you begin to accumulate frost again on the lunar night side. A couple interesting things to note. At the equator, this frost doesn't completely ablate until about 16 degrees in longitude past the dawn terminator, which means if you could see this, you should see this strip of white frost along the dawn terminator. At the poles, you actually don't fully ablate this frost during the daytime. So you should actually end up with these polar frost caps at either pole. Now, this process doesn't ultimately prevent a significant amount of ice from reaching the true polar cold traps represented by those diviner temperature maps. Essentially, as the atmosphere becomes depleted in water vapor, this process is going to become less and less important. The frost layers are going to become less and less thick until they stop forming at all. But this is just kind of an interesting note on some weird phenomena that might have been happening at this time. So now I'm just going to wrap up with some conclusions before we go to questions. So our model finds that volcanic ice delivery could be comparable to that of impact. So we find that around 8 × 10⁻15 kilograms of ice end up being delivered to the lunar poles in our model. And around 10 to 16 kilograms are delivered via impact. So comparable. The we find that this volcanic period was probably characterized by many short-lived collisional atmospheres. So not something like the Needham and Kring atmospheres where you have one big atmosphere that lasts for a really long time, but these short-lived atmospheres that are nonetheless collisional. We find that water is removed from these atmospheres very quickly due to both photodissociative escape and ice accumulation, but of course, a significant amount of ice accumulation takes place. And then we find that the fractional ice coverage ends up increasing towards the South Pole, but not the North, and that the South Pole ends up with twice the ice mass of the North. This is consistent with these crater shallowing observations by Rubinenko et al. In 2019. So overall, I would say our model paints this picture of volcanism and ice accumulation on the moon, and suggests that volcanism could have been a viable source for this polar water ice, especially old and deeply buried ice. Now, I will note that this is a complex system we're modeling here. There are plenty of knobs to be tweaked with this model, and a lot of nuances that I think are interesting to discuss here. But again, this is the general picture that this work is painting. So with that, I think I'll stop myself and open it up to questions.
Awesome. Thanks, Andrew. Really cool work, really cool presentation. So yeah, we have plenty of time for questions. I see some applause, and I see Jim has a hand up. Jim, go ahead.
Yeah, really excellent study, very nicely presented. Just curious about what you were assuming for the volatile content of individual eruptions, total volatile content.
It's a great question. I think I have that here. So we assume this kind of 667 ppm, which from my reading on most of the literature is kind of a median value, but obviously there's a huge range of predicted outgassing water contents, right? It extends from like 10 parts per million, almost no water, to 3,500 parts per million. And I think that there's a lot of nailing down to do of that number. That's my impression anyway. And honestly, actually, I'd be really interested to hear your perspective on what this number maybe should be.
Sure. Yeah, I think two things. One, you might clearly there's evidence for quite a lot of variation in individual eruptions. By that I mean compositionally related, so that one of the things you might do is to introduce kind of a, I don't know how you would do a random number or some kind of algorithm to introduce variability there, so you actually capture the larger ones too. Because we certainly see, significant pyroclastic deposits that clearly have been energized and propelled by more volatiles than normal. So yeah, I'd be happy to talk about that more too, and in general, as a suggest some next steps there. Second question I had was you mentioned the sorry, I'm a little slow this afternoon. I got up at 2:30 this morning to give a talk in Moscow. So you mentioned the residence time polar ice and permanently shadowed areas. You were talking about a billion or so years. Did I get that right?
Yeah, in the permanently shadowed areas that are cold enough. Yeah.
One of the things we've been working on recently is the question of true polar wander, and I'll send you a paper we just did in PSJ, which talks a little bit about the variability. That it might be interesting to look at that when you look at your final estimates for the total volumes in different areas. So yeah, that's great. Really nicely presented, and I'm sure if one of your committee members disappears, I'd be happy to pitch in and help out. Okay.
Well, you're totally invited to come to my my talk. It'll be hybrid, so you're welcome to come see it.
Well, best of luck. I'm sure you'll do well. Thanks.
Thank you. Yeah, that just to kind of follow up on that, the polar wander question is an interesting one, and I've talked to Matt Siegler about that a good amount, because he's done some work on,
Right.
you know, polar volatiles and true polar wander. And I think there's it'd be interesting to try to nail down when exactly that happened. You know, did it happen before most of this volcanic stuff occurred, or did it happen afterwards? And if it did happen afterwards, you know, by that point, was a lot of this volcanic ice either destroyed by other means or, you know, mixed in with regolith and potentially protected via lag layers or what have you? I think there's a lot of questions to ask there.
Yeah, what we did was we basically used Grail data and looked at the distribution of craters as a function of time and size, and then looked at how they would affect essentially the position of the pole. So it's kind of incremental. It moves around is the thing. So I'll send you a copy of that one.
Yeah, that'd be great.
Thanks.
All right, so we'll go to David, then the chat, and then to Tim. But yeah, David first.
So good talk. I have some concerns about the physical model of the gas dynamics.
Okay.
The CO doesn't condense even at night, right?
Correct.
So is the CO atmosphere dense enough to carry heat around the planet? That is such that the diviner maps would not really be valid.
Yeah, so we actually assume that because CO is radiatively neutral, it doesn't affect surface temperatures. Also, one thing to keep in mind is that these atmospheres are extremely thin, so they're still collisional, but we're talking about atmospheres with surface pressures of like half a microbar. So like 10 times or like 1,000 times or 10,000 times thinner than Mars's current atmosphere.
So, okay. Because it seems like the photodissociation timescale of water at 1 AU is about a day. And so the way you're going to not photodissociate away everything quickly is if it ends up condensed on the night side and then just rises near the dawn terminator. So it seems like the devil's in the details of modeling the gas dynamics of that atmosphere of a two species atmosphere along a dawn terminator, and what happens to the water in this. It's convecting, there are winds and so on.
I think one of the key things limiting the photodissociative escape rate is the fact that the escape due to photodissociation, we're assuming, is essentially happening at or above the exobase. So it's not at any one time, it's not all of the water in the atmosphere that's, you know, exposed to photodissociative escape. So even though the escape photodissociation is extremely efficient at 1 AU, you know, it's not all of the water that's being, you know, exposed to that process at any given time.
But you just to assume that, you got to assume that the water which is photodissociated below that exobase, wherever that is,
It's recombined.
Doesn't escape because it recombines.
Mm-hmm.
Is the pressure high enough to allow for that? Recombination rates, that's between, you know, H and OH, that is kept in the flow. Is that really adequate, those pressures?
That's certainly that's one of the assumptions we're making. Definitely that essentially that water photodissociated below the exobase does recombine. But I think you bring up a really interesting point about I think that the chemistry that could be going on in these atmospheres is really interesting, the photochemistry essentially. And I think that is certainly an avenue that needs to be explored more.
Have you, maybe I don't want to dominate here, but have you validated one of your situations against a highly detailed simulation with a lot of physics in it?
You mean like a GCM or like a photochemistry model?
A GCM that incorporates photochemistry and, you know, kind of the stuff Parvati did in the past.
Mm-hmm.
Even if it's with a continuum model.
So we've compared like at least some of our assumptions to some work that Igor Alinov has done with GCM modeling of atmospheres like this. Essentially, I think in that 2019 paper, they focused on atmospheres similar to the Needham and Kring atmosphere, so a lot denser than what we're talking about here. But in subsequent work, I've seen it like AGU and LPSC, they've modeled atmospheres this thin, so getting down to a microbar. And they're finding that I don't think they incorporate any of the photochemistry, but they are finding that dynamically, these atmospheres are extremely efficiently mixed. So you end up with essentially pole-to-pole Hadley cells, similar to what we see on Mars seasonally, and you know, essentially very, very efficient transportation of water to the poles, which suggests to me that, you know, potentially this 50-year timescale that we're talking about for water being taken out of these atmospheres might actually be on the longer end of the spectrum than what they're seeing in this GCM modeling.
Okay, let me not dominate here. Thank you.
Thank you for those questions. They're great questions.
All right, good practice for your defense. All right, so we have and I'll just say I haven't looked at since David mentioned some of the stuff I'd done previously. You know, I mean, I haven't done volcanic eruptions. Like my comet eruptions were not comet eruptions. My comet impacts were pretty small compared to the scale of these eruptions. But yeah, but I think, you know, that would be a really interesting problem to look at. But I think Andrew, your response is correct that you know, like, so you're kind of like at the state of the art here, and comparing to the Alinov GCM simulations and stuff. You know, I mean, like they seem to be sort of consistent as you know, as far. I mean, there's always like more. Like one can always get more detailed with the physics, but I think, you know, considering where the physics is at, it's promising that all of these different things seem to kind of behave consistently. All right, so Rosemary Killen had a question in the chat. Other loss processes are sputtering, photon simulated desorption by Lyman alpha, and impact vaporization. Did you consider those processes?
Yeah, photodissociative by Lyman alpha, that is included in our photodissociative model.
And I guess this is I'm guessing, and Rosemary can correct me if I'm wrong, I'm guessing this is related to so you showed how if you account for sublimation over 4 billion years, the ice thickness reduces. So I think this is sputtering photon stimulated desorption of the deposited ices.
Of the actual deposited ice.
Rather than the atmospheric.
Yeah, so we haven't passed like a kind of back of the envelope calculation sense. We haven't looked at these loss processes once the actual ice is deposited. So we're looking at some of these in the atmospheric escape, but not actually the ice deposits themselves. So I think like you can think of those maps I showed you as kind of the net ice that could have been supplied. And then once it gets there, I think there's a lot of interesting questions about what could happen. Basically, does it stick around? Does it accumulate fast enough that it doesn't get totally destroyed by, you know, micrometeor bombardment, photodissociation, sputtering, that sort of thing? I think that's one of the next steps of this modeling work for sure.
All right, and Tim has a hand up.
There I am. Thank you. That's a good talk. I have a challenge for you. I was intrigued by your slot, your graph where you show the amount of water per unit area or per just per zone that you have distributed with latitude. and show the north and the south poles very different, because we do have measurements with LEND and the neutron remote sensing, and those numbers are just exactly similar on the north and the south. They are right parallel. They end up at the same number on the area average.
You're talking about this figure right here?
Yeah. Yeah.
Okay, great. I didn't know that.
So that was, I presented that at the DPS last week. So I can send you my slides from that, and that'll be at the Polar Volatiles conference coming up in Boulder too, although I'm just going to be virtual for that one. Also, yeah, with respect to the last couple of questions and how much detail you need to put into removal and retention processes, this is something I brought up with Deborah Needham a few years ago too, with you suggesting a volcanically produced atmosphere, and she was using an atmosphere of CO2 and H2O, and making the assumption that once you've had a photolysis event, the particles are lost. But the reason Mars has retained a substantial atmosphere today is because there are chemical recycling reactions between photolysis of CO2 and photolysis of water that recycle it back into CO2 and water molecules. So that would slow the removal process at least. So that's something we can't just ignore chemistry. It happens, and it's a powerful effect in the universe.
Yeah, absolutely. We've already touched on this a little bit, but I'm very curious about the chemistry of these atmospheres, and I don't claim to be an atmospheric chemist, but I think there's a lot of nuances to be explored with that respect.
Yeah, I have a dissertation or two I have to go read to bone up on the subject.
Me too, apparently. Cool though. Yeah, I would love to see those slides. And I'll be at the Polar Volatiles conference. So I'm looking forward to that talk.
Okay.
Right. So Jim, I see you have a hand up. I'm not sure if that was from earlier or if that's a new question.
It's a residual hand.
That's a residual hand.
I'll get rid of it here.
Right.
But
Residual hand deposit.
Andrew, can you shout out your email? Are you so I can send
I can put it in the chat right now.
Okay, that's great. Thanks.
All right. What other questions do we have? Okay, Cesare. Wait, Cesare, you're I think you're still muted.
Okay, maybe now?
Yeah.
Can you hear me? Okay, good. Double muted. So very interesting talk, and I was thinking about what you said about the liver of volatiles. You find that these eruptions have the liver water, which is comparable to the cometary bombardment or asteroid, but yet in the end you find so thickness, which is consistent with the model from Rubanenko et al. So I was wondering if do you think that the one source dominates the other one, like cometary and asteroid delivery versus eruptions, or one happened before the other, and so you see then that one dominating the other one? Because I would expect if you have both sources comparable, would you expect a thicker deposit than what you find?
That's a really good question. So I'd say there's potentially a couple of things going on. One of the things I'm not clear on, and maybe Parvati has a good answer to this, is whether or not the distribution of ice you should end up with would be similar in the volcanic case versus the impact case. Because the volcanic case, because it's this atmospheric process where you can make the reasonable assumption that water vapor pressure is similar across the surface. Essentially, it should be directly the thicknesses of deposits you get and the distribution of ice should be directly related to where the cold traps are, right? That's going to be the dominant process. But I'm not sure that that is also true in the impact processes. So, you know, say if you have an impact that, you know, leads to ice being distributed, not necessarily at the pole. Is it going to eventually get to the pole, and is it going to kind of overlap with this volcanic ice? Second, I doubt that that all of this volcanic ice, it would be possible to retain all of this volcanic ice, right? So even though our like average amount is enough to account for that crater shallowing with Rubinenko, I think it's compelling that it's enough. But I also think that, you know, if you did retain most or all of this volcanic ice, you know, that implies that you should have, you know, 400 meters, a 400 meter thick ice deposit in some of these very coldest cold traps. And I don't think that, I think maybe that could be the case, but I doubt it. So I think that there's definitely some destructive processes going on. And you know, what that would mean is that even if you did have multiple, you know, impacts and volcanic ice supplying, volcanic outgassing supplying ice, potentially that's why you get to this, you know, kind of Rubinenko values. Sorry, that was kind of a rambly answer. Did I answer your question?
Yes, thank you.
Yeah, this is super interesting. Like I feel like we won't, but I feel like we could easily go another hour. And related to the question you just mentioned, Andrew, like I was smiling because I had written down here, like so one question I was gonna ask you is, so when you're sampling your volcanic eruptions, does the location of those matter at all? Like, is that a parameter, or do you assume that, you know, a volcanic eruption occurs and then within your time step, it's already global?
We assume the latter. So
Okay.
essentially, it doesn't matter where the eruption occurs. It occurs fast enough that in one time step, you create an atmosphere. Yeah. And we assume that it's occurring fast enough, and essentially baked into that assumption is also that it's like the eruption isn't violent enough to, like, you know, release that vapor into a huge cloud, which I think is a big difference maybe between these volcanic eruptions and like the impacts that you've modeled, right?
Right. Yeah. That's a good point. And I guess also in yours, you know, if I guess the time scale of accumulation is much longer than the time scale of the eruption itself, and so, you know, maybe the location doesn't matter that much, and that's a good enough assumption.
Yeah,
but yeah,
one interesting point I'll add to that too is even if the initial location of the eruption did matter, one of the interesting things, because these different ice reservoirs that are at different temperatures can essentially communicate with each other via the atmosphere. Essentially what happens the longer one of these atmospheres persists is the coldest cold traps steal ice from the warmer cold traps. So even if, like, you know, your ice initially was mostly in this kind of region, eventually it should be transported to the very coldest regions. That's a function of how long the atmosphere exists, but that certainly is a process that's going on.
awesome. All right, so we are coming up on the hour, so I'm gonna call into the questions there, but Andrew's email is in the chat, so feel free to reach out to him if folks have more questions. And let's see. All right, Kristen says good luck on Friday, and I will repeat, good luck on Friday for your dissertation defense. And in case you didn't hear this at the beginning, Andrew is currently looking for postdocs. So if you have any leads, I'm sure he would appreciate them. And we mentioned this the Lunar Polar Volatiles conference came up a few times. I put the link in the chat. It sounds like several folks are going to be presenting, and that should be an interesting meeting. And it looks like there will be time for discussions there as well. So yeah, so hopefully we'll hear more interesting volatiles related science there in a few weeks. And for next month's meeting, I haven't done this yet, but I was going to reach out to folks who are attending or organizing the Lunar Polar Volatiles conference, and maybe also the Apollo Sample Analysis conference that's later this month. And I'm thinking if they're available, maybe for our November meeting, we could kind of recap the latest and greatest from those meetings, and perhaps from DPS as well, which I didn't make it to, but from Tim's comments, seems like there was some interesting stuff there as well. But otherwise, we are right at
there wasn't a lot of moon. There wasn't a lot of moon at the DPS.
Okay.
You didn't miss much.
All right. I'm sure we missed lots of other interesting stuff.
There was a lot of Uranus and Dart and Venus and so many things.
Nice. Yeah, I heard it was a good meeting. Yeah, awesome. All right, so it's 5 p.m. on the East Coast, so we'll call it a day. Thanks everyone for dialing in. Thanks, Andrew, for a really good presentation. And yeah, good discussion, everyone. And we will see each other at some point in the future.
Great. Thanks
Take
again,
care.
folks.
Good luck. Bye-bye.